Let me welcome you to this lecture. We have been discussing about silicates and we have seen how we can classify the silicates based on how the SiO4 units in these silicates are connected. If the SiO4 unit is discrete, or if discrete SiO4 units are there, then we classify these silicates as orthosilicates, and if two SiO4 units are connected together through one by sharing of one oxygen atom, then we call such silicate minerals with composition Si2O7 6 minus ion are present in these silicates, and we call them as pyrosilicates. Then we have seen if two uh, oxygen atoms per SiO4 tetrahedra are shared, then we can have formation of either cyclic silicates as well as a simple sane silicates, which are also called pyroxenes. So we will now extend our discussion on silicate minerals, and we will see what other types of silicate mineral structures can be formed by sharing of more number of oxygen atom per SiO4 tetrahedra. So we have the last silicate that we discussed is a simple sane silicate, where there is only one individual chain is present, that is formed by sharing of two oxygen atom per SiO4 tetrahedral. Let us draw this. And we have also discussed that depending upon after how many SiO4 unit the repeating unit comes, the structure of such silicates, same silicate minerals can be different. And here we are drawing a chain silicate where the repeating unit appears after every two SiO4 units. So this is what is simple chain silicate, and this is going to form infinite polymeric chain structure in this way. Now what can happen is that two such same silicates can join together, and that is going to form double chain silicates. So what can happen is that these two individual chain silicates can get joined together by sharing of oxygen atoms, and that will lead to formation of double chain. So we can draw the structure of such double chains here. Let us draw the structure of a double chain silicate. So this is how the chain can get extended, or two chains can get joined together, and double chain silicates are formed. These are also called amphiboles. Sorry. And how the two chains are joining together, these two chains are joining together by sharing of how many oxygen atom between the two chains essentially decide or essentially that leads to formation of different types of chain structures. So we have chain structures which are based on decomposition, as well as we can have chain structures which have decomposition as well, and chain structure, sorry, this is 17. So with this formulation are also quite common. So this particular composition, or this particular chain composition, essentially these minerals are known as asbestos minerals. So what we have seen is that asbestos is a double chain silicate. Now within this double chain, the SiO linkages are quite strong, and In the lattice, what happens is that these oxygen atoms which carries uh, negative charges, they on the surface they will have these oxygen atoms will be essentially present as OH groups, and on these OH groups metal ions are going to bind, and that is how the lattice is essentially formed, that is of such double chain silicates. Now since within the chain or within the double chain the SiO linkages are strong, and that is why and the linkage of these double chain to the metal ions are quite weak as compared to the SiO bond strength, and that is why when these double chain silicates cleave, they cleave as fibers, and that is why these double chain or silicates or amphiboles, they are of fibrous nature. We know that asbestos has many applications because of its fibrous nature. So we'll now proceed further and then see what kind of silicate minerals are possible when more than two oxygen atoms are shared per SiO4 units. So if we can have formation of seed silicates, that is two-dimensional. Seeds are of two-dimensional nature, so we will have extended structure formation along two particular directions. In case of say chain silicates, we have seen that the extension or polymerization is happening along one particular direction. But if we have polymerization happening in two directions, then we have formation of two-dimensional structure, and then sheet silicates are essentially formed. And for formation of sheet silicates, what is important is that three oxygen atom per SiO4 tetrahedra are shared, and when it happens, then we have formation of seed silicates. So let us try to draw the seed silicate. So we have already extended along this particular direction, say along x direction. So now if we extend along y direction, then we will have formation of seed silicate, and what we can do is that we can extend on this particular picture itself, and then we will have formation of seed silicate in this way. So we can go on extending the seed structure in this particular fashion. So this is what is a simple sheet where there is only one sheet of this SiO4 tetrahedra which share three oxygen atom per SiO4 tetrahedra is formed, but such silicate minerals with only one single sheet of silicate are essentially quite rare. What we have, or what generally are common, are where there are more than one sheets are present, which are stacked one over the other. Say, for example, we can relate the structure of such silicates with the structure of graphite, where there are hexagonal sheets of carbon atoms are stacked one over the other. Here also we have two or three such sheets of SiO4 tetrahedra are essentially stacked one over other in most of the seed silicate minerals that are known. While such simple seed silicates, which we can relate with the structure of graphene, where there is only one single sheet of hexagonal carbon atoms. So we can relate this with the structure of graphene. Now, depending upon how many layers are present, these structures are going to be different, and there are essentially 4 different classes of seed silicate minerals are known. So the first one is clay minerals. Then we have white asbestos. Then we have mica, and number 4 is montmorillonite. So these are the 4 different classes of sheet silicates or seed silicate minerals, which have their structures are different because the number of sheets that are stacked together are different in all of these. Now, if we look at the structure of such seed silicates, say 2-dimensional structure, if we look from along the edge here, so this is the 2-dimensional sheets, and on top of these sheets on one side there are OH groups are present. So these oxygen atoms which are not shared, which are unshared, the central oxygen atoms are yet unshared with any other SiO4 tetrahedra, and that is why they are present as OH groups here. And now if we look at the structure of, say, aluminum hydroxide or magnesium hydroxide, what we will see is that these are also layered hydroxides. The structures are again layered, and the structure is again sheet-like structure. And if we look at the arrangement of or special arrangement of the OH groups in the layered structure of AlOH3 or magnesium OH2, then what we will see that the 2/3 of OH groups here in aluminum hydroxide or in magnesium hydroxide have essentially same arrangement like the OH groups present in this sheet silicate structure. So what happens if we take a AlOH3 layer? So this is AlOH3 layer over the sheet silicate structure over here, say Si2O5. Then what is going to happen is that some of the OH groups are going to lie exactly on top of each other in this way. So what can be done is that if we do condensation, so here we have on both the sides, that we have to remember that the OH groups in AlOH3 say are present on both the sides, while some of the OH groups on AlOH3 are going to match or will lie exactly on top of OH groups present in this sheet silicate structure. So when we do condensation, what is going to happen is that these OH groups are going to get condensed, and then what is going to form is a special type of sheet silicate structure where we have AlOH3 layer and we have this Si2O5 layer stacked together in this way. Of course, this will also have OH groups on this side. So the mineral that is formed will have composition of Al2OH4 Si2O5. This is going to be the composition of this mineral, and this is known as kaolinite. This particular mineral is known as kaolinite. Now what we can do is, because we have also OH groups on the other side of this AlOH3 layer, so what we can do is we can these are all connected by oxygen atoms in this way. So again, if we put another seed silicate on the other side of the AlOH3 group over here, So we will have formation of this sort of silicate structure where two Si2O5 sheets are essentially staked, or this ALOH aluminum hydroxide layer is essentially sandwiched between two such silicate sheet structures. And here we have three sheets are staked one over the other. The first one is silicate, the next one is aluminum hydroxide, and the third one is again silicate. And this is again this another silicate mineral which is Al2OH2 Si2O5 2, that is the composition of this silicate mineral, and this is known as chrysolite. Sorry, this is known as pyrophyllite. This is known as pyrophyllite. And now, apart from aluminum hydroxide, we can also put magnesium hydroxide. And if when we put magnesium hydroxide instead of aluminum hydroxide, we will have again similar type of seed silicate formation can happen. So in this case, the formula is Mg2OH4 Si2O5. This is the formula, and in this case, the formula is going to be Mg3. Here it is Mg3 because magnesium is divalent metal ions, so it is going to be Mg3. And now this particular mineral is known as chrysolite, while this is known as soapstone. And this mineral, soapstone, this is white asbestos, also known as white asbestos. And this soapstone, it is quite lubricating in nature. It is slippery in nature, and that is why it is used as a dry lubricant. So this is a lubricant. So we have seen the different types of sheet silicates and how we can modify these sheet silicates by using appropriate metal hydroxides, and then this leads to formation of different industrially important silicate minerals essentially. So let us now look at what is going to happen if we are going to share all 4 oxygen atoms of SiO4. We have seen so far that the kind of silicate minerals that are formed when we share 1 oxygen atom per SiO4 tetrahedra, 2 oxygen atom per SiO4 tetrahedra, as well as 3 oxygen atom per SiO4 tetrahedra. And now we'll see what is going to happen when all the 4 oxygen atoms are shared for each of these SiO4 tetrahedra. And in that case, you can visualize that when we share two oxygen atom, then we have formation of one-dimensional same structure, and when we share 3 oxygen atom per SiO4 tetrahedra, we had formation of 2-dimensional sheet structure. And if we are going to share all 4 oxygen atom of SiO4, but we will have formation of a 3-dimensional silicate structure. And the formula of such silicate is going to be SiO2. So we have the pure form, we know it as quartz, as well as many other phases are also known of SiO2. So now in case of such 3-dimensional silicate with composition SiO2, we do not have any metal ions, and what we can do now is that we can do isomorphous replacement of some of these silicate ions in the three-dimensional structure by using an metal ion which has a similar radius, that is Al3 plus. So if we remove Si4 plus by Al3 plus, what is going to happen is that now in SiO2 it is electroneutral, but the moment we replace some of the Si4 plus ions with Al3 plus ion, the framework or the three-dimensional structure is no longer going to be electroneutral, because we have reduced the number of positive charges here, and that is why the framework is going to become anionic in nature. And now what we can do is that we can replace either one quarter or one half of these Si atoms in these silicate three-dimensional silicate structures, and depending upon that we can have two different types of such three-dimensional silicate minerals can be formed. So in the first case, when we replace one quarter of silicon atoms we have formation of this sort of mineral, where out of 4 silicon, one is replaced by aluminium, and we can also replace half of the silicon, one half, and in that case this is going to be the formula. So now for these sort of silicate minerals, there are three different types of silicate minerals, essentially having three-dimensional structure. The first one is feldspar, which are essentially part of these rocks. So these are very dense silicate minerals, and there are no hollow space, or there are no pores are present in these four feldspar minerals. Then we have another one which are called zeolites. Now in case of zeolites, these are less dense as compared to feldspar, and there are channels are honeycomb like channels are present in zeolites. And in these channels, the cations are going to be present. So the cations are going to occupy these channels, and apart from that, the channels are quite large in nature, and then water can also reside in this channel, as well as other small molecules can also reside in such these channels present in zeolite, and that is why zeolites are essentially used as molecular sieves, because they can absorb water into these empty channels, and that is how zeolites can act as molecular sieves, as well as they are also used as ion exchangers, because within these channels cations can be present, and that is why these cations can be exchanged with other cations, and they are used essentially as ion exchangers as well. So because of these reasons, zeolites have been studied quite extensively, because they have a lot of applications here. Apart from that, the third category is known as ultramarine, because they are called ultramarine because their color is splendid blue. Very intense blue color is there for these minerals, and the reason why they for this intense blue color is because they also have other anions apart from the silicate ions. There are also other anions present in these ultramarines, and the formula of such ultramarines, we can one formula we can see is so in these ultramarine we see that the sulfide ion S2 ion is essentially S2. This is S2 2 negative ion is present, as well as we can also have sulfate or chloride. These sort of ions can also be present in ultramarines, and because of presence of such anions within the silicate lattice, the color of these minerals are quite intense blue, and that is why they are called ultramarines essentially. So these are different types of three-dimensional silicate minerals. So this essentially brings us to the end of this lecture. What we have learned in this lecture is essentially what kind of silicate minerals are formed when we share more than 2 oxygen atom per SiO4 tetrahedra. We have seen that by sharing of oxygen atom, double chains can be formed, because for formation of simple chain only 2 oxygen atom per SiO4 tetrahedra needs to be shared. But when these single chains essentially get condensed by sharing of oxygen atoms, then we have formation of double chains, and in these double chains there are some of the SiO4 units share 3 oxygen atom, while some of the SiO4 units share 2 oxygen atom, and that is why they have this formation of double chain structure. And these minerals are also called amphiboles, we have seen. And one good example of these amphiboles is asbestos, and because the double chain structure is essentially very rigid or very strong, or within the chain the SiO bonds are quite strong, while the double chains are interconnected through metal atoms. Because of the presence of OH groups in these double chains, they interact with metal ions, and that is how they are interconnected. But these metal interaction with metal ions are essentially weaker as compared to the intra-chain SiO linkages, and that is why when these double chains cleave, they cleave as fibers, and that is the reason why asbestos has many industrial applications because of its fibrous nature. Then we have seen if we share 3 oxygen atom per SiO4 tetrahedra, then there is formation of sheet silicates, and we have seen different types of sheet silicates. That is, we have seen that we have clays, and then we have also as white asbestos, and then we have mica and montmorillonite. These are the 4 different types of sheet silicate minerals. And finally, we have also seen the how we can, in case of these sheet silicates, we can modify them by using other layered materials, because the sheet silicates, the OH groups present on one side of the surface, essentially they can be condensed with other layered hydroxides, and that leads to formation of different aluminosilicate sheet minerals. And we have also seen examples of such aluminosilicate minerals. So one of them is kaolinite. Then we have seen also pyrophyllite, and then white asbestos, which is known as chrysolite, and then last one that we have seen is sandstone. Then soapstone, sorry. And then finally we have discussed what the kind of 3-dimensional structures that are formed when all the 4 oxygen atom of SiO4 tetrahedra are essentially shared, and the basic structure or basic the most simple silicate mineral that is formed when all 4 oxygen atoms are shared is SiO2, where there are no metal ions, but then isomorphous replacement of the silicon atoms with aluminium leads to formation of anionic framework. And depending upon the how these anionic frameworks are formed, essentially there are 3 different types of 3-dimensional silicate minerals. The first one is feldspar, which is dense, and there are no pores in these minerals, which are at these form these constitute the rocks or stones. And then we have zeolites, where there are honeycomb-like hexagonal channels are present in these zeolites, and within these channels water molecules or small molecules can be inserted, and that is why they are used as ion exchangers as well as molecular sieves. Then the last 3-dimensional silicate we have discussed are ultramarines, where there are other anions like S2 negative, and because of which there is a characteristic blue color in these 3-dimensional silicate minerals. So with this, let me conclude this lecture, and I thank you very much for being with me during this lecture.